What do you have?
Wait, one of us do this.
Do you have a plug in it? Okay.
There you go. So this is the first lecture of the evidence-based medicine series, the way we're going to try it, we've done this many different ways, and we're going to do it a different way today. So we're going to arrange it so that one of the EVM faculty will do a statistics lecture without math. Don't worry, no math, very little math. For the first 15 minutes. Then the idea of evidence-based medicine lecture series is to teach you how to critically review an article. So I'm going to send out an article, and we're going to use the Center of Evidence-Based Medicine checklists to find the bias in the article. Every article I send out will have at least one bias, and it's kind of like a clover hunt to the small groups. So you're going to break up into small groups, and you're going to use the checklist to define a bias. And the resident who's doing the lecture will, I will tell them the bias before, and give them some literature on the bias, and they will explain how the bias will affect the interpretation of the paper, and the risks of the bias in the paper, and how those biases affect the results of the paper, and why you should be aware of the biases. So today, we're going to talk about data types. Why do you want to know about data types? Because if one day you actually do research, which I could only hope, you're going to have to know the data type to first define which statistical test to use. The other reason to know data types is that if the author of a paper you're reading has used the wrong data type, then you can throw the paper out immediately, because if you mix up the data type, you've mixed up the statistical test, and you've mixed up the interpretation of the paper. Don't go any further. They've used the wrong data type, and they've used the wrong summary of the data type, the central tendency and the variability for the wrong type of data. Throw the paper out. Don't even bother going through anything else. So that's what we're going to talk about today. There's two types of data, continuous and categorical. So we're going to discuss the two subtypes of data. Then I'm going to talk about how to describe interval and ratio data using central tendency and variability. And finally, we're going to talk about how samples get to populations. This is the heart of statistics. 1733, a French guy named de Meaux came up with the central limit theorem. Actually, it wasn't called the central limit theorem until the 1920s. But the basis of statistics is the ability to tell from a sample of the population something about the whole population, right? You can never actually study 100% of the population. It's impossible, not feasible. Everyone with hypertension you could never study. All research and all statistics are based on taking a sample from the population. And how you get from the sample to a guesstimate of the population is the central limit theorem, which I will never go through the math with you because you lose consciousness almost immediately. But it is a very important concept that the sample, also, when you talk about the statistics, you're talking about estimating a population from a sample. How good that estimate is determined by the sample size and the variability of the sample that you collect and the number of times you sample the population. So, but this is key to statistics, is this central limit theorem, which I'm just going to talk about in very broad terms. You're going to go forwards. So there's continuous data and categorical data. Under the continuous data, there's interval and ratio data. On the categorical data, which are chunks of data, is nominal and ordinal data. So continuous data is from 1 to infinity, or 0 to infinity. It's that every interval between 7 and 8 is the same information as between 122 and 123. So the intervals are fixed, like a temperature scale. The intervals are fixed. Height, weight, lactate, troponin are all examples of continuous data. Interval data does not have a natural zero. It's not so important, the difference between interval and ratio data. Ratio data, as we're going to talk about in a minute, has a real zero. Examples of interval data is temperature, at least in Fahrenheit and Celsius, doesn't really have natural. 0 Celsius and 0 Fahrenheit doesn't mean there's no temperature. Actually, 0 Kelvin does. We're going to talk about that in a few minutes. pH, SAT scores are all examples of interval data. Ratio data, and the only importance about ratio data is you can make proportions out of ratio data because it has a natural zero. Interval data, you can't have a percent temperature, right? You could have a percent temperature change, but you really can't have a percent temperature. But you can have a percentage of Kelvin, a percentage survival rate, a percentage flow rate, right? Where things have a natural zero. Like troponin can be zero. It's not just less than, it can be zero. Or lactate can be zero. Categorical data is chunks of data that's divided up into specific groups. And in those specific groups, we count the number of the number of participants in each group. So you could have age, race, age group, educational label, for examples of categorical data. And there are two types of categorical data. There are nominal data, where just a label is placed on the data groups, but there's no order to the data groups. So there is Likert scales, there's ethnicity scales, right? There, Amazon rating, you know how many stars, right, a product gets, which you know is all false because it's, you know, some company who makes the product is paying someone to write a lot of reviews, right? So that's really bad data. But that's so. And ordinal data is where it's ordered. The labels are ordered, like Likert scales, like Amazon scales, right? How many stars you get is ordered. 3 stars aren't as good as 4 stars. 5 stars are better than 4 stars. But there's no, between 3 and 4 and between 1 and 2, although it's numbered and it goes in some order, the interval makes no sense in the real world, right? A 2 scale isn't half as good as a 4 scale. It really isn't. I mean, it may look like that, but in the real world and what they mean, it's not. And that's what ordinal data is. So I wanted you to kind of guesstimate with me what the scale is. How about the serum sodium concentrations? What's the scale? Is it ratio, interval, nominal, or ordinal? It's ratio, right? Because you can have 0. And weights in Brooklyn? Weights in Brooklyn? Ordinal, interval, nominal. It's not nominal, right? It's not categorical. So it's either ratio or interval. Can you have a 0 weight? It's certainly not in Brooklyn, right? So this is interval data. How about pain scales? Pain scales, 1, 2, 3, 4, 5 pain scales, up to 10. Is it ordinal, nominal, interval, or ratio? It's ordinal because there's just a label to the amount of pain, right? And it's ordered. But the difference between a pain scale of 1 to 2 is not the same as between 2 and 3. The amount of pain, it's just a way of categorizing it, categorical data. And blood type? Blood type, A, B, and O, and RH, and all this other stuff. It's nominal because we just put a name, we just put a label on something, right? And those have important implications on how you describe the data, the central tendency, and the variability. So whenever you look for data to be analyzed, you should produce 3 different characteristics for every data. The central tendency of where the middle point is, the variability, and the shape of the distribution. So whenever you produce a data point, a summary data point, there should be 3 characteristics: the central tendency, the variability, the distribution of the spread, and the shape of the distribution. So the central tendency is broken down to 3 different criteria. The mode is the most common number in the group, the most common element. The median is that 50% is above that number, 50% below that number, and the mean, which is the arithmetic mean. So which is very prone to outliers. So if you have a whole group of numbers and one number is way out to the edge, which happens all the time in clinical medicine, which would be most sensitive? The mean, right? Because it's the sum divided by the number of participants, right? So when you have data that's not normally distributed, you probably shouldn't use the mean, right? And we're going to talk about what normally distributed means is you could make a histogram of the data. And this is probably, there are statistical tests to see if it's normally distributed. But most statisticians say, looking at a histogram of the data, and a histogram of the data is just looking at the chunks by interval and the number of patients, the number of subjects in each chunk. And this is how the world works. If you do a large enough sample, actually this is one of the tenets of the central limit theorem, is if you sample anything enough times, the samples will always run in a normal distribution. This is how the world works. Why this works is a very complicated mathematical solution, but this is accepted kind of as an axiom now, that if you sample the population enough times, the means of the samples will have a normal distribution. So if you have interval or raw data, you can summarize the central tendency as mean, median, or mode. All three are acceptable. But if you have ordinal data, like a Likert scale, right? Or ordinal data like Amazon number of stars that a product gets. And Amazon makes this mistake all the time because it tells you the average number of stars that a product gets. Well, the average, the mean, has no meaning where the intervals are not the same. Between 2 and 3 and 3 and 4 is really not the same meaning. So averaging them has even less of a meaning. So ordinal data, you should never have the mean. So if you see a study that produces Likert scales or survey data, you know, better than, less than, I like this thing, I didn't like this thing, and then they have a mean, well, then you should probably throw out that paper because it's the wrong way to describe the data. And if you don't know how to describe the data, you probably made 12 other errors in the study. Nominal data, of course, there's no mean blood type. There's no median blood type, right? But there is the mode, which is the most common blood type. And affected by the outliers, the mean is the most sensitive to being affected by the outliers. So let's talk about the next term, is the variability, or the error term. So variability is a natural process of how the world works. Anytime you sample something, you're going to get some high numbers and some low numbers. But there's also, that's biological variability. Experimental errors, blunders, biases. There's lots of reasons for variability. But there is 3 ways to determine, like there were 3 ways to describe central tendency, there are 3 ways to tell about variability. And each way is determined by the data type. So range is from minimum to maximum. That has got to be the easiest way, right? Minimum to maximum. Interquartile range, we said the median was 50% of the data. What point of the data is 50% greater and 50% less? Interquartile range is 25% and 75%. So it tells you that 25% of the data is below this number, right? And then 75% would be greater than the data. Or that the 75% less, or 75% greater. And then standard deviation is the average distance from the variability from the mean. The average distance from the mean. So when should you use this? So this is a normal distribution. And you can see in a normal distribution, the mean should equal the median, should equal the mode, right? And skewness and kurtosis, skewness tells you how many tail, the length of the tail. Negative skewness is the negative tail that way, positive skewness is this way. Kurtosis is how pointed or how flat it is. So you can describe by these skewness and kurtosis is a way of calculating a normal distribution. And it's important that normal distribution, there are certain statistics that are contained and necessary for normal distributions. Certain statistical tests can use not normally distributed data. So again, you have to know the type of data, the variability of the data, if it's normally distributed or not, to tell you which is the proper statistical test. And if you come to me with a set of data, that's what I'm going to do. Is we're going to explore the data using histogram, and we're going to visually inspect, and we can do some statistical tests to see if it's normally distributed or not, and we can calculate skewness and kurtosis, and there's an absolute number that's related to normal distribution. And then knowing that and the data type and the number of groups, that tells you which statistical test to do. Remember, statistical tests are now all computer driven and there's a graphical user interface. So too many people have access to statistical tests. So they can do any statistical test in any paper until they get a p-value less than 0.05. And this is a very common error in the medical literature that slips by reviewers all the time, by the way. So if you have interval data, well, then you could do the range. You can do range, interquartile range, and standard deviation. Ratio data also, for the same reasons. You could report the range, the interquartile range, or the standard deviation. Ordinal data, well, you can produce the range, the interquartile range, but you certainly cannot do standard deviation. It doesn't make sense. For ordinal data, it just doesn't make sense to do means or standard deviations because the interval between any two numbers has a different meaning in the universe. And nominal data, well, you could report the range, but certainly not the interquartile range or the standard deviation. So this gives you what you should do. Any questions? Because we're going to go into a different subject. So the central limit theorem, again, this was the basis for all what we call frequency statistics. 1723, a guy named Devos, and then codified into the 1920s. Laplace had something to do with this in the 1800s. But the central limit theory is the most important theory in statistics because what it does is it says that I can guesstimate the central tendency and the variability of the population just by randomly sampling the population. Randomly sampling. So this is a big deal, randomly sampling. All statistics is based on this idea of randomly sampling. So unless you really do a really good job of randomly sampling the population, the statistics are going to be biased. So just about all emergency medicine research and most medical research is very difficult to randomly sample because, especially in emergency medicine, because, you know, it's mostly a convenience sample. It's when the people are there to do the research. But the central limit theorem connects the sample to the population. What it does, the idea of the central limit theorem is that if I randomly sample the population many, many times, the means and the standard deviations of the samples will come close to the population sample. So if I just sample the population frequently, frequent statistics, many, many times, I could guesstimate the central tendency of the population and the variability of the population. And the error of that is the confidence interval that you've all learned about. So the confidence interval is different. What we've talked about now is data types of the sample. But now we're going to use the central limit theorem to go from the sample to the population. And the way we report that is the confidence interval. We report the central tendency of the confidence interval, which now has the word point estimate. And the confidence interval, the width of the confidence interval is determined by a few factors. One, it's determined by the sample size. So as I increase the sample size, the confidence interval will equal the variability or get close to the variability of the population. And that's the other thing that determines the width of the confidence interval is the variability in the population. If the population is very variable, well, then the confidence interval will be very wide. If I take a large enough sample, I'll just get to that variability. But this is the most important idea in statistics, that you can go from a sample to guesstimate the population. And that's it. That's the whole lecture. So we talked about the continuous and categorical data. Continuous data was broken up into interval and ratio data. Categorical data was nominal and ordinal. I taught you mean, median, and mode, range, interquartile range, and standard deviation are the ways to describe the data. And we talked about the central limit theorem, where I can go from a sample to a guesstimate of the population. There's the late Ernie, was reading the kidney. I disturbed him. He was reading about GFR, I think. Any questions?